Welcome to Module 8, in which we will discuss electrochemical process design and make the step from single electrochemical cells all the way to a complete electrochemical plant. The learning goals of this module are the following. You should be able to select a suitable electrochemical cell for a certain process. You should be able to make mass balance calculations over the electrolyzer, make heat balance calculations over the electrolyzer, design a stack from a number of electrochemical cells, and design the complete process around the electrochemical reactor, and make an overall mass balance for the complete plant. And here in this picture you basically see the interplay between all these components. So you have the electrochemical cell being part of a larger electrochemical reactor. We need power input into this reactor. We typically have power conversion for that. And we have a number of surrounding unit operations around the electrochemical reactor that help in the conversion of the raw materials to the products. We start with the heart of the electrochemical process, which is the electrochemical cell. There are quite some types of electrochemical cells, and here we will discuss them. So let's have a look. We already discussed in the module on laboratory techniques that a parallel plate cell is the cell that most closely resembles industrial electrochemical cells, and it does. And here you see such a typical parallel plate cell in which you have a membrane which separates the anode and the cathode compartment. But there are more types of electrochemical cells. Namely, here we have a closed cell, which is typical of a battery. There we don't have a flow like in the parallel plate cell. No, it's a closed system where we have a porous anode material and a porous cathode material. Another typical cell is the tank cell, which is often used in the world of plating, in the world of metal production, where you just have a tank and you have an anode and a cathode hanging in there. For example, here you see copper plates. And of course, next to the divided parallel plate cell, where you have the membrane, you can also have a parallel plate cell without a membrane. This is, for example, the case for the sodium chlorate process, where you want the product that is formed on the anode to react with the product from the cathode to form chlorate. There are more types of electrochemical cells that are similar to the parallel plate cell but are slightly different. For example, the zero gap cell, which we already discussed in our module on 3D electrodes. In that cell we have these electrode meshes that are pushed against the membrane to minimize the distance between anode and cathode and hence reduce the ohmic resistance in the electrochemical cell. Then there are also cells in which there's a gaseous reactant. And these cells need gas diffusion electrodes. Well, they can be designed in a couple of different ways. For example, this is how a fuel cell is designed, where you have both oxygen and hydrogen coming into the cell, and you have here a layer of electrode, the membrane another layer of electrode. Basically, the gases can react at the electrode, and for example, then the protons are transported through the membrane so that at the other side the other gas can react. It's important to note that even though it seems that this cell is dry, it's not. You always need to humidify the gases to make sure there's enough water in the electrochemical cell present, because basically electrochemical cells need water to function properly. There are also other types of gas diffusion cells. You can see one here. On the left side you see the anode, but that's just a normal, basically the half of a zero gap cell. There's no gas diffusion reaction here. So the interesting part here is on the right side, and there you see again a gas coming in, you see a gas layer, but here you now see a separate liquid compartment. And that is, for example, needed if you also form a liquid product here. And this is, for example, the case in the oxygen depolarized cathode process used in the chloralkali process. Now, the last type of electrochemical cell I want to discuss is the electrodialysis cell, and I will do that a bit more in depth in the next slide. Here on this slide, you see a small electrodialysis stack, and in the middle, you see the electrodialytic cell. And in contrast to other electrochemical processes, there are no electrodes. So there's no anode nor a cathode in the cell. Instead, there are just ion selective membranes. An anionic change membrane, which allows the transport of anions, and a cationic change membrane that allows the transport of cations. The electrodes are only positioned at the end of the stack, and they basically make sure that you get the potential gradient you need to have the driving force for the anions and cations to go through the membrane. Now, how can you use electrodialysis? It's typically used to dilute or concentrate salty streams. So if you, for example, go with a stream into this cell, you see that it could contain some salt. See that the anions want to go through the anionic change membrane, and the cations go through the cationic change membrane. So as you go through the cell, you dilute the electrolyte. And the opposite applies here, that if you go through the cell, the anions go into that stream, and the cations go into that stream. So you concentrate this stream. So that is related to the fact that these membranes are ion selective. And that is so electrodialysis can, for example, be used to make clean, potable water from brackish water. When designing an electrochemical process, you might wonder, what cell should I use? There's a lot of common sense involved in that, but you can also use a couple of these rules you can see here on this slide. For example, first question you should ask yourself, do I need to separate the anolyte and the catalyte or not? If I need to do that, then I need a divided cell. If not, then I need an undivided cell. Is it a continuous or a batch process? In a continuous process, I will need a flow cell because there are streams coming in and coming out. It's a batch process. I can use a batch cell and there's no need for in and outgoing streams. Is there a gas as reactant? Then I do need a gas diffusion electrode. Is energy consumption really important? If so, we really need to minimize the ohmic resistance and we typically go towards zero gap cells. If not, we can go for what is called a finite gap, which basically means there's a gap between the electrode and the membrane. Do we need electrodes in every cell? Yes, then it's a normal electrolytic process. If not, if there's no purpose of the electrodes, because for example we want to do an electrodialysis process to make a very strong concentrated salt stream, then obviously we go for an electrodialysis cell. Do we need a high electrode area? Yes, then we can go for 3D electrode. If not, we can go for flat electrodes. And an interesting one is, do we need a robust or an efficient process? Is it all about reliability? So I just want to make sure that it always works? Or do I really want top performance? And this can make you make different choices. For example, if you want something robust, you typically take thick membranes because they cannot break easily. And you might want to apply more distance between the anode and the cathode to avoid any short circuits. If on the other hand, efficiency is really important, you like thin membranes with a low ohmic resistance, and you want really to minimize the distance between anode and cathode. So these just give you some general indications to help you in selecting the most suitable cell for a process. But as said, it's a lot of common sense using your electrochemical expertise to design the cell. Now, this is where I would like to finish this first screencast of this module. Thank you for your attention.